So so good afternoon, everybody, and thank you to Fast Markets and Phil for this opportunity to share some of our thoughts from Dastur on basically the decarbonization challenge in front of steelmakers. I'll talk a little bit about Europe, but our experiences are fairly global. So we keep an eye out on developments everywhere and engage with clients everywhere to advance clean energy transitions in multiple industries, but specifically in obviously the steel industry as well. So next slide. Oh, go ahead. Yeah. So just a quick introduction to our organization. We've been a private consultant to the steel makers for almost 60 years, Dastur has been. And over the last 5 or 7 years, we've made a significant transition into investing in the clean energy transition space for industrials. And so the core domains that we work in are hydrogen, carbon capture, methanol, basically the carriers of clean energy. And we bring kind of an engineering background for many years, as well as expertise in techno-economics, markets, et cetera, to pull together feasibility and viability solutions for steel makers. We work also with governments on policy issues, so a lot of analytical work and engineering design work. So next slide. So some of the recent projects that are in the public domain that we can discuss a little bit about to give a flavor of the kind of work we do. We're currently engaged in a very interesting and very impactful, we hope, project to capture a couple of million tons of carbon dioxide at Burns Harbor, one of the very storied plants in Burns Harbor, Indiana, which is a 5 million ton steel plant. Many of you are familiar with. Which is the first carbon capture project, by the way, in the U.S. At a blast furnace at this scale. We just finished up, or very close to finishing up, the first carbon capture project at a refinery in India, which is the U.S. Trade Development Agency project. Just finished up another project a couple of months ago on petcoke gasification in India, also for a large refiner. And we also did a large-scale carbon capture and clean energy from petcoke project in Abu Dhabi National Oil Company, which is the 7th largest oil producer in the world, capturing about 5 million tons of carbon dioxide for use in enhanced oil recovery. And we finished that up just as a couple years ago, just as COVID was getting started. And so these are all feasibility studies or pre-FEED design works that we've done. And so we get involved in the initial conceptualization, the design, the FEED, and we are really not tied that way to any technology provider per se. We work with multiple technology providers to do these studies on behalf of clients. So specifically, as you know, I won't go over this too much, but as you know, steelmaking generates a very substantial part of the industrial emissions. Industrial emissions make up a quarter of the total emissions in the world. And steel makes up about a quarter of that. 7% is the average, is the number across. We see various studies that we've done. The cap, and specifically when we talk about Europe, the cap and trade, the ETS schemes, the scheme that is in place and that has been increased recently. Results in approximately, we think across the steel makers we work with, about a 30% reduction by 2030 in terms of their carbon footprint for integrated steel makers. So that is a very large, a large motivator to basically accelerator to basically make decisions and choose the right path in terms of moving forward. A part of this, the battle really is, there are several things that are complicating the situation here. One is the change in regulatory landscape, both in the US as well as in Europe, and the emerging landscape in places like India and China. In the U.S., as you know, there's a 45Q scheme in place that basically grants a tax credit of about $50 for sequestration of carbon dioxide and $35 for enhanced oil recovery for injection into wells for enhanced oil recovery. That number is changing. It's not clear whether it will change, but there's obviously a strong push to increase it to $85, the $50 number. In the Europe, the ETS cap and trade numbers have also been changing, and there's been an increased push to increase the level of carbon capture over the last, and I think the targets for to 2030 are going up recently quite a bit. So that's driving a lot of the activity. We talked about the 3 process routes. I won't go into detail, and these are kind of the overall numbers for capture. When you add up the different contributors, obviously the lowest is the EAF route. Then there's a natural gas DR route, which results in 1.2 to 1.4 million tons of carbon dioxide per ton of steel produced. And then the BF-BOF route, and that really includes kind of the complete, all the emitters possible, which includes sinter plants, coke oven batteries, the BF, and the blast furnace, of course, is the largest emitter in that picture, in kind of the integrated plant picture. Now the numbers in the U.S. are a lot better, and the numbers at plants that we've been talking about, like SSAB or Imuden, who we'll talk about in Europe, they're much better. So some of these are some of the best plants in the world, and many of those plants have significantly lower carbon footprints than the numbers you see here. These are global averages. The World Steel Association average, I think across all the plants, is about 1.8 or 1.9 tons of carbon dioxide per ton of steel. So that's across all the different kinds. So this is the range of numbers. So when we look at the different paths taken by the different players, we see, I'll talk about some of the recent developments. ArcelorMittal, as you know, recently moved away from a blast furnace carbon capture project, and they've moved to switching to an EAF, and also to kind of they have been going for a while at their Ghent project, a carbon to methanol project, which is very interesting. And they were actually going to do about 3 million tons of carbon capture and storing it under the North Sea, and they've moved away from that and into this. We're involved at the project at Cliffs that I mentioned, that is a DOE study with Cliffs to design a carbon capture project for the blast furnace, the Burns Harbor blast furnace. The one project on the DR, on the EAF that is actually implementing carbon capture already is the Emert Steel project that captures about 0.8 million tons of carbon dioxide per year. That has actually been in operation since 2016. We're also involved in a DR project in India in Jindal Steel and Power, which has gasification and is doing carbon capture. And then you heard directly from SSAB. There's Tata Steel Imuden, which is again recently committed to a hydrogen route for carbon capture on their blast furnaces at Imuden. So there's a range of different approaches taken by the different players, and I think I'll talk a little bit about the Burns Harbor project because that's something that we're very close to, and we see a lot of opportunity there for that to be replicated at other blast furnaces. But the Burns Harbor is a 5 million tons primary steelmaking operations. It's a very large-scale operations. And we plan to reduce the carbon emission from the blast furnace by about 70%, capturing about 2.8 million tons. And we plan to do it in a process that keeps the cost of that neutral to the 45 tax credit regime in the U.S., which gives you about $50 of credit. The project uses proven carbon capture and gas processing technologies for both carbon dioxide capture as well as for hydrogen separation. The hydrogen separation will currently be used for clean power. It'll just go into the powerhouse for now, replacing natural gas. But over time, as you see that the demands for hydrogen will increase and the types of uses of hydrogen in the steel plant will increase, we expect it could be used for other things, such as maybe someday hydrogen-based blast furnaces, direct injection into the blast furnace, for example. Our current cost of the project based on the technology, the numbers that we have are about $46 per ton. That includes CapEx amortization, and that also includes about a $10 cost approximation for transport and storage offsite for that carbon dioxide. So in the different directions that folks have taken and that we also are engaged with several steel makers in conversations, there are several challenges that were talked about earlier today. Specifically, if we're moving to gas-based DRI, hydrogen, again, we're talking of large projects where there's more than, let's say, at least 1 million tons of production, and correspondingly, about 1 million tons, in the DRI route, there's about 1 million tons of carbon dioxide coming out for 1 million tons of production. So there's a need to implement CCUS or find a transition to hydrogen, and as the panel just before me just talked about, finding 1 million tons of hydrogen at an acceptable cost point is extremely difficult, even in the next 2-3 years. It's really difficult. And secondly, for gas-based DRI, as you know, the cost of gas, well, right now the cost of gas is very high everywhere. But even if you assume a longer-term natural gas price of about $3 per MMBTU in the US, the corresponding price in Europe would be about $7-8 even with the gas that's coming in from Russia and Ukraine, that pipe gas. So the cost of the gas DRI has to be taken into account in terms of figuring out the economics for that route versus kind of carbon capture on an existing primary steelmaking route. Secondly, if you talk about hydrogen-based DRI, the largest pilot for pure hydrogen DRI is about 100,000 tons per annum. And so it really needs to scale up very significantly before, 1 to 2 million tons of DR facility can actually run entirely on hydrogen or very largely on hydrogen. And I know that our friends at Midrex have made a lot of progress, and so we keep abreast of the literature and the latest development. But it's definitely, for somebody to make an investment decision about a multi-million ton production primarily based on hydrogen as a clean fuel, it's a challenging, I think it's a difficult decision. Again, if you're talking about green hydrogen, I think the previous panel, there were some good numbers about the scale of hydrogen production, and I have a slide about the cost of green hydrogen. But basically about 100 megawatts is the largest plant today at Emuden, which is one of the Tata Steel facilities. And that's about, I think for the 3 million tons, that's about, I think, 1/10 of the total electricity that they need. So the total volume of hydrogen is an issue, just as is the cost. So if you're trying to make a decision today on the route that you want to go. Scrap EAF, if you're moving to EAFs, as you know, Algoma announced and many companies have announced incremental investments in EAF technology. As Lorenzo pointed out earlier in his conversation this morning, and Phil as well for World Steel Dynamics, it's a very substantial jump in the total volume of scrap that's going to be demanded by the market a few years down. And it's not clear exactly how price will, whether the scrap volume will be able to actually expand to meet that demand, and how that will be reflected in the price. And again, blast furnace carbon capture is not without its challenges. So in blast furnace carbon capture, steam and electricity, so the largest capture technologies are amine-based. There are other technologies like oxy-combustion or cryo-cap that we work with also, but the technologies that's most popular are amine-based, and they have a high steam and electricity content. So that you need to figure out what is the cheapest way to get that steam and electricity to keep your capture costs under control. And again, hydrogen injection into BF, there's a lot of interest from steel makers we deal with on that, but really that technology also is not ready for a bet on by somebody who is producing any substantial volume. So here is the range of cost. This is a U.S. Department of Energy study from 2020 that showed the costs of hydrogen production from different routes, right? And if you look at anything that's green, which is, if you can start from nuclear electrolysis, it kind of goes, and this is dollars per kgs, it goes from, anywhere from, 5, 6, 8. So even if you take about $4 as kind of the lower bound as to where it will be in the near term, it results in about a cost of about $200 for the hydrogen alone that's needed. So today, and that's not viable obviously from a cost of production standpoint. So today, in the near term, really this is not an option for somebody who is, a large-scale steelmaking operation, we feel. Again, this is kind of percentage of electricity in Europe that is coming from renewable sources. There are some exceptions like Sweden and Iceland and Ontario in Canada that have very respectable percentages of renewable electricity due to various geographic reasons. But across Europe, this is the EU 27, people are often surprised to know that in 2020, barely 20% of the electricity is renewable, and this is a EU projection. It's supposed to go to only 30% by 2030. So, so you either have to figure out, so you can't rely on your scope 2 emissions really being green, because the percentage of electricity the grid is not going to provide you that, basically. So one of the advantages of carbon capture is that there are a relatively large number of sites. Of course, now this number has to increase by 100 times in 5 years, or many times in 5 years. But there are, as of now, 27 facilities across the world. This is according to the Global CCUS Council that tracks all the live projects that are capturing 36 million tons of carbon dioxide as of September 2021. And they're spread across different industries, from natural gas processing to ethanol to power generation has a lot of carbon capture. But the core technologies are the same, and they've actually been deployed. So the cost, the economics, the challenges are fairly well understood for carbon capture technologies. So in summary, the messages are carbon dioxide and decarbonization is the goal, and not people get focused on kind of green versus blue. The only thing to really measure is what is the carbon capture. Is carbon capture actually happening, and can you operationally do it from the economics that you have? No point in basically coming up with something that is too green but is very unlikely to get implemented in, let's say, the next 3 to 5 years, and it's not a viable solution. Successful pre-2030 projects in the industry, given the new cap and trade regimes, require approximately a 30% decarbonization, and the risk mitigated way to do that is the main challenge we feel in front of steelmakers today. Gas separation technologies, carbon capture, are proven across multiple industries. It's still early days for the steel industry for capture at a blast furnace at a coke oven battery, but it's the technologies have been used extensively. Carbon dioxide does not have borders, so as Lorenzo mentioned and others mentioned, the basically policy coordination and ensuring that the right trade protections are in place are a must to ensure that the enforcements in Europe and the U.S. are actually funded and are not basically quote unquote carbon dumped from outside. And with 70% of the global and 60% of the EU production being in the blast furnace route, looking at all of that cannot transition over to it's not practical or feasible for it to transition over to either DREFs, or some of it can, but a lot of it cannot. So focusing on the CCUS route and finding the economics for that is the key, and we look forward to actually working on this problem for some time to come and finding viable solutions for steelmakers that are trying to do that. Thank you.